So we found the domain. We set the denominator equal to 0 and solved each of those. That got us the things x couldn't be. And then we simplified by canceling the matching factors out. So this one was already factored for us. They're not going to be.
So that's it.
Then that would be the final answer. Now, what I want you to notice here is if we simplified first, we'd lose part of our domain because we don't have two pieces in the bottom. After we simplified, we only had one piece. So we would lose part of our information about the domain. So that's why we got to find it first. Domain's got to be found first. Then you can simplify. Factoring is going to be the vehicle for simplifying these things. That's why we did the lab tonight, to try to review some of that stuff. If we can factor it, then we can get the things that are the same to cancel out. And that's what we're trying to do, is make the fraction in simplest terms. Just, like if you had 8/12, you'd reduce that to 2/3 because 4 goes into both 8 and 12. It's simplifying a fraction is all it is, reducing a fraction. These happen to have polynomials in them instead of numbers. Okay. All right, let's look at another one. Same instructions. We're going to find the domain, then simplify. Remember, they're going to ask it in the other direction. They're going to say simplify and then find the domain. But we know better. We know that if they give me something like this, I'm going to find the domain of that first. Okay. So to find the domain, what do? Set the denominator equal to 0. X squared minus 25 equals 0. So there are many ways to solve that. There's solved by square roots. There's quadratic formula. There's all those things. You want to factor it because you're going to have to factor it anyway. Most of the ones you're going to get are going to be factorable. You're going to be able to factor them. So you want to think about factoring. That's why, this whole idea, reason we're going over that tonight. Well, 5 and -5, because this is a 2 terms. It's 2 terms, so it's a difference of squares. So my factors are x plus 5 and x minus 5. And then solving those, we get x plus 5 equals 0, x minus 5 equal to 0, and we get x equals -5, x equals +5. Those are things x cannot be. So our domain is all x's as long as x does not equal plus or minus 5. That sure is a nice way of writing that, but let's write it in interval notation as well. Negative infinity to -5, -5 up to +5, and then from 5 to infinity. There's our domain. That's how we found the domain of that. Now, the reason we factored that is because when I go to do my simplifying, the bottom part, I can rewrite it, instead of writing x squared minus 25, I've already done the work of factoring it, so I'm going to use that factored form. Okay? And the factored form is x plus 5 and x minus 5. Doesn't really matter which order you put that in. But then I want to try to factor the numerator, the top part of that. So it's trinomial, so it's an x method deal. So multiply to be 5 and add to be -6. Good. X minus 5, x minus 1. Because that's 5, or my -5 and -1, filling in the x. That helps us because what's going to cancel out now? The x minus 5s cancel each other out. You've simplified x minus 1 over x plus 5 with the domain that we've got over here. We're simplifying it. Okay? It's not that bad. They get a little bit more complicated with the polynomials, and we're going to do some of those. But again, not such a big deal. So if they ask for the domain, when are you going to find that? First, always. Okay, so domain is found first before you do anything else. All right, now, if they just say simplify, which there's plenty of that happening, let's just practice simplifying a few. Don't worry about domain. We're just going to simplify. That gets us some more practice factoring. Over 4x squared minus 25. So we're not finding domain on this. We know if we were, we'd set the denominator equal to 0 at the beginning. But we're not, so we're going to simplify. So let's factor, which one are you going to factor first, top or bottom? Top's fine, yeah. Why do we factor the top? What's the first thing you always look for? Which is? And an X. What's that leave left in those parentheses there? 2x minus 5. Okay, denominator. Look out. Doesn't matter what order you write those in. I wrote the plus first. Then, what cancels? 2x minus 5. 6x, 2x plus 5. That's now this 6x and this 2x cannot cancel with each other because of the plus 5 here. That makes those different. Okay? You can't cancel individual pieces like that. You can only cancel things that are multiplied. Never can you cancel things that are added or subtracted to one another. They can only be multiplied. So that's why the factoring happens there. Okay? No, that's what I'm saying is you can't. Is the 6x and the 2x can't be done because the 2x has the plus 5 tied to it. So that makes it a whole different monster. So they can't be done like that. All right, so let's try this one. X squared plus 8x plus 16 over 8x minus 2x squared. Kind of complicated just a tad here. Writing the bottom part in the wrong order. Let's see if that can cause us a problem. So what do we do here? Can we do the top part? Yeah, X method on it. So we're looking at 16 and 8. Yeah, it's X plus 4 twice. Candace is pretty quick at this. That's good. Now what happened on the bottom? Okay, a 2 and an X. And because that is in the wrong order, that 2 on the front of the X squared is negative. I'm going to pull that negative with it. So that's going to be what? Plus X. Yeah, or X minus 4. We'll write it that way. Does that simplify any? Can you cancel any of that? The factors don't quite match, do they? So it won't simplify. So you just leave it like that. That happens sometimes. But you got to factor it to make sure on that. So the factoring is still got to be done whether it simplifies or not to even know if it would simplify. If you don't factor it, you're not going to know that it doesn't simplify. So you got to factor it anyway. So that's the factored form. Your book may leave it in the original form just because it didn't do that. But the factoring had to be done sometime in the background to know if that would even simplify or not. Sometimes they do, sometimes they don't. Most of the time they do. There's going to be rare that they don't. But it is possible. So I threw that one in there. All right, so let's try this one. 2x squared plus 7x minus 4 over 5x squared plus 20x. Again, we're just trying to simplify that. Okay, X method on top, which would be negative 8 and positive 7. 8 times negative 1. Good. So I'm gonna have to do a little extra work here because I can't go straight to my factors. I got to do some grouping. So the top one, that's got 2x in common, x plus 4. What do I pull out of the second group? -1, and that changes that to x plus 4. So my factored form on the top would be what? You mean, yeah, just 2x minus 1. Good. Now let's factor the bottom. I didn't do anything with it here, so I'm just going to go to the next step. What's the method we're going to use there on the bottom? Yeah, which would be 5x and x plus 4 left in the parentheses. If we were told to find the domain, what would we do? That's right. Set 5x and x plus 4 equal to 0. If they told you to find the domain, you do that now instead of later. Okay? Because what's going to cancel out? Yeah, the x plus 4s cancel each other out. So we're left with a 2x minus 1 on top and 5x on the bottom. And again, you cannot simplify a 2x when it's got a minus 1 on it with the 5x on the bottom because they're not the same. Okay. So far, so good. All right. Let's look at taking a couple of rational expressions and multiplying them. Okay. Let's take 6x to the 6th power over 7 times 28 over 9x squared. Okay, so we're multiplying fractions. A couple of different ways to do this. One way would be multiply first, simplify last, which works okay, but it's not going to extrapolate to the more complicated problems. So we got to remember our rules for multiplying fractions. For multiplying fractions, the rules are that you can simplify up and down or diagonally, never straight across. So we can cross cancel diagonally or we can cancel vertically. Those are our options. Okay. So if we look at both of these and we try to do vertically first, are there any vertical, like the first fraction doesn't simplify any? The second fraction, 9 and 28, they don't simplify.
We can do diagonal.
But diagonally works really nice because 6 and 9 are both divisible what? By what? 3. So this becomes a 2. This becomes a 3 by dividing those by 3 each. And then what about the x squared and the x to the 6th? It's got an x, 6 x's up top and 2 x's on the bottom. Not divide the 6 by 2. What's the rule for exponents when you divide? Subtract. That's right. So 6 minus 2 would be 4. So these two cancel 2 of those. So there's x to the 4th left over. What about the 7 and the 28? All right, and 7 is really a 1, but it cancels it completely out. So once we've gotten that done, we're just multiply straight across. So 2 times 4 is 8 x to the 4th. On the bottom, 1 times 3 is 3. We get that done. Okay. All right. Let's try another one that's kind of like that. 4y squared over 18 times 27 over 8 y to the 5th. Okay. The 4 and the 8, yeah, that's an obvious one diagonally. 4 goes into itself once, and then the 8 twice. So it's the 3 y's are left where? Yeah, down here in the bottom. That's right. So this is cancels out and makes that to the 3rd power. What about the 18 and the 27? Is that the biggest thing that goes in both of them? 9's bigger, so we're going to use that. 2 and 3. So on the top, we got 1 times 3 is 3. The bottom, we got 2 times 2 is 4. Y to the third. And we've simplified that multiplication problem. So not too bad. I think these are harder than the ones where we're factoring. We're about to do those. These are harder because there's more pieces to look at. The factored versions like this, I'll scroll up so you can still see that one, where you've got something, maybe you've got x plus 4, x minus 3 in the top over maybe one that's x minus 3, x plus 3 times another one that's got maybe x plus 5 in the top and x plus 4, x minus 1 in the bottom. Everything's factored already in this problem. We're going to get to some that are not, but we're starting with one that's factored. So we want to cancel out things that cancel the same way that we did the previous two examples, vertically or diagonally. So vertically, do I have some? Go ahead, Reese. The x minus 3s, they cancel each other out. Diagonally, the x plus 4s cancel each other out. So the only factor that's left on top, x plus 5. The factors that are left on the bottom, x plus 3, x minus 1.
So then you're just playing with the entire factored answer.
Yes, you're canceling matching factors that are vertical or diagonal and get whatever's left and leave it in factored form. Really not bad. Let's look at this one. 4x squared plus 3x minus 10 over 2x squared plus 3x minus 2 times 2x minus 1 over x plus 4. So obviously not in factored form. So we have to put it there. Which ones will factor? Well, does 2x minus 1 factor? No. Does x plus 4 factor? Mm-mm. So it's just that one fraction we got to factor it. So we're factoring this trinomial right here that's got a 4x squared and a minus 10. Okay, so we're looking at the x method to do that. So negative 40 and add to be 3. What might do that? 2x plus 5 and 2x minus 2. How are you getting there? Guessing and checking it? Okay, so 2x, you said 2x plus 5, and that's the question. Is it right? Does it add to be the right part in the middle? Okay, so on our x, it has to be 8 and negative 5, right? And if we do 4x squared plus 8x minus 5x minus 10, we can factor out a 4x and get x plus, we can get x plus 2 in there. And then a negative 5 there, get x plus 2. So the factored form of that 4x squared plus 3x minus 10 is 4x minus 5 and x plus 2. I know what you're doing, Candace. I learned it that way. I learned it by guessing the two pieces and then checking it to see if it works. That takes a while if you don't get it right, especially when the numbers get larger on each end. It makes it tougher to, you got so many options. If you guess the right one the first time, great, you're faster. But most of the time, you don't guess the right one first off. So the X method keeps you from guessing all evening. That's the reason I do it like this. I learned it the way you were doing it. That's how I learned to factor in high school. I don't do it that way anymore. I don't teach it that way at all because you could end up if the first number is a 32, you got all the options for 32. You got 2 and 16. You got 8 and 4. You got 32 and 1. You got several options for 32. And if the other number on the other end is a 24, 24's got a lot of options. It's got 2 and 12, 3 and 8, 6 and 4, and 24 and 1. So it's got so many options that unless you have it perfect, you're going to keep guessing. So this is where that X method kind of, and doing the grouping, can speed you up a little bit. Maybe not on every problem. If you can guess it right on the first try, maybe it's okay. But on the big picture, I think it's better to go through the grouping way. All right, let's graph. Let's factor the bottom part. So 2x squared plus 3x minus 2. So if I do the X method for that, that's -4 and 3, 4, -1. So I've got 2x squared plus 4x minus 1x minus 2. So there's a lot of scratch work involved here for this. That's going to be 2x, x plus 1, -1. I mean, not x plus 1, x plus 2. Sorry. -1 and x plus 2. So the factors are 2x minus 1 and x plus 2. I need to change the color of this fraction part. It looks different. And then I didn't have to do anything to the second fraction. So let's cancel what shall cancel. 2x minus 1 here cancels this one up here. X plus 2, top and bottom. And that's it, right? 4x minus 5 or x plus 4.
So really, if you dumb it down, it's just puzzle pieces and you go.
It's factoring and finding the pieces that cancel out. Yeah, finding the puzzle pieces that go away.
Okay. And I'm guessing if you get, say, 2 pieces on the top and bottom of the final answer, you get something wrong.
No, not necessarily. Everything on the top could cancel out. Everything on the bottom could cancel out. Okay. That's possible, and it just leaves a 1 in whatever spot that happens in. It's not necessarily wrong if that happens, because that does happen some. All right, let's look at division. So when we divide fractions, what was the method to do it without a calculator? So I'm gonna just do a quick example with just numbers. So if we're gonna divide, if I were gonna divide 2/3 divided by 15 over 4. Yeah, it's 2/3 times 4 over 15. That's how that works. You're always going to flip the second one and multiply. This one doesn't simplify any, so you're just going to multiply straight across. So it'd be 8 over 45, which doesn't simplify at all. When we're dealing with what the material we're in, we might have 5x squared minus 16x plus 3 over x squared plus x minus 12 divided by 30x squared minus 6x over 2x to the third plus 8x squared. You're still going to factor everything the same way you did with multiplying. The only difference is you got to flip the second one before you start canceling. So, I'd factor this one, I'd have x. This one is easier. The bottom part's easy on this one, so it's x plus 4 and x minus 3. Top part's not quite as easy because we need 15, -16. So that'd be -15 and -1. That stinks. That'd be 5x minus 1 and x minus 3. If you group that, pulls out a 5x, and there's the x minus 3. The next one pulls out a -1, so that's x minus 3 left in there. So that's where I'm coming from for those factors. The second half, you've got to flip it and multiply. So when I factor that, I'm going to write it, I'm going to flip it over. Okay. So this factors is 2x squared, x plus 4. And it goes on the top. And then the 30x squared minus 6x. 6x would be what's in common. So it's going to be 5x minus 1. And that goes on the bottom. So you're still factoring the same. It's the same game once you flip the second one. And you start canceling things that cancel. It's that and that. This and this. This and this. So here's one of those, the question you were asking about, well, what if everything cancels? Well, look at that whole thing over there. It canceled. So everything's gone in that first fraction. So all we got left is 2x squared over 6x. 2 goes into itself once and into 6 3 times. This x squared is one of those x's cancels. So all that's left is x over 3. That big ugly Mama Jama there for a problem.
What did you
This 1x in the denominator canceled one of the x's in the x squared.
Okay.
So it's like subtracting exponents. 2 minus 1. Left that 1x up there at the top. So that big ugly problem we started with simplifies to be x over 3, which is very nice, a lot easier to deal with if we're going to do something with it later on. Just where we're going anyway. Okay, so division is exactly the same thing as multiplication. You just got to remember to flip the second one before you start. And then it's back to the same game. All right, now, so we did multiplication, we done division. Guess what? This next with fractions, adding and subtracting, which is fun. If I'm going to add and subtract fractions, let's say I was going to add 3/5 plus 9 over 20. If I'm going to do that without typing it into the calculator, what do I have to have? The same denominator. Okay, so what denominator would 5 and 20 have? 20. What times 5 gives me 20? 4. So whatever the bottom gets multiplied by, the top gets multiplied by the same thing. So that's going to be 12 over 20 plus 9 over 20. So that would be 21 over 20. Okay. So common denominator is going to be the name of the game that we're trying to build here. Let's put one that's got some letters involved. Say we had 3 over 10 x to the 4th plus 2 over 15 x squared. And one of the things that can help you here is to over here on the side, LCD is liquid crystal display. No, lowest common denominator. Or least common denominator, maybe what you called it in school. Least common denominator means the smallest thing that both of those will go into. 30 is the number. What about x's? Which one has the most? 4 of them. So it means I can't go below 4 of them. So I need 4 of them. So the LCD would be 30x to the 4th. So what I've got to do is work toward turning the denominators into that. Okay, so the first fraction gets multiplied by 3. Doesn't need any x's. No, it just needs the 3. So the top gets a 3. The second fraction, it's got a 15, so it needs to be multiplied by 2, and it needs 2 more x's to make 4 of them. So that's the x squared. So the top gets that as well. And then when you work that part out, you get 9 over 30x to the 4th plus 4x squared over 30x to the fourth. And then you simplify by adding the numerators. 9. I'm going to write it in descending order. 4x squared plus 9 over 30x to the fourth. You're supposed to look at that and see if it'll factor and then cancel anything that will. It doesn't factor. There's not anything that they're all divisible by. So
would it just be plain 30x to the fourth on the bottom because they're both the same?
Yeah, the denominator, when you're adding, subtracting, denominator doesn't change once you get it the same.
Okay, so
Once you get it the same, leave the denominator alone.
just move it over.
Just move it over.
Okay.
The numerator is the only thing that should change. Okay. We're looking for what number does 10 and 15 both go into? That's the 30. And then your variable, you got an x to the fourth power and an x squared. There's no way to make the fourth power go down, so I've got to bring the second power up. So you're always going to pick the bigger one for part of your least common denominator as far as that goes. Let's look at one that's maybe it's got a factor in the denominator. Maybe it's 7 over x minus 5 minus 2 over x minus 5. The denominator already the same, right? So what happens? Just subtract the top. 7 minus 2 would be 5. What's the denominator now? Just x minus 5. Okay. Now, let's get to one where we got to do a little work. All right. This one, they're a little bit sneaky when they do this to you, because they're almost the same, but they're not. Okay. What's the difference in the two denominators?
Position.
Yeah, and the sign of them, right? So like in the first one, the 3 is negative. In the second one, the x is negative. So can I factor anything out of this second one to turn it around? Think about how we factored when there was a negative in the middle. If I pull out a negative 1, that's going to make the x positive and the 3 negative. And then I can think LCD. Well, the first one has an x minus 3. The second one has an x minus 3 and a negative 1. There's no way to get rid of the extra stuff, so you've got to tack it on to the one that doesn't have it. So the least common denominator is going to be negative 1 x minus 3. So the first fraction needs what part? The negative 1. So I'm going to multiply bottom and top by negative 1. That's going to be negative 6 in the factored form on the bottom. I didn't change anything in the second one because it already had the stuff. And then I'm just working that out. So I got negative 2, negative 1, x minus 3. And I can actually simplify that now. Because negative 2 divided by negative 1, yeah, positive 2 on top, x minus 3 on the bottom. Because these two can divide. Because they're regular numbers. So that kind of baby stepping us into factoring to fix this. Let's look at this one. Let's do 4 over x minus 3, x plus 5. So I'm going to give you the denominators in factored form already. And then plus 6 over x plus 5, x minus 5. All right. Denominators are already in factored form. That's key. that if they're not in factored form, I want to try to put them that way so that I can start looking at it. So here they're in factored form already. So I look at the factors. What's the shared piece? What do both of them have? So that's got to be part of the LCD. The shared piece shows up the one time because it's shared. And then any piece that's not shared shows up in the LCD. Okay? Shared piece and everybody else. So what's everybody else? What's the first one have that's not shared? X. It's got the X minus 3. And then the second one has what part that's not shared? It's got the X minus 5. So that's part of the LCD as well. Okay? Then to go and fix the fractions, you got to look at it and say, okay, this one had the X minus 3. It had the X plus 5. What part did it not have? It didn't have an X minus 5. So it needs an X minus 5 on top and bottom. The second fraction had 6 on top. It had an X plus 5. It had an X minus 5. What part of the LCD did it not have? An X minus 3. So that's the part you got to put on there. Okay. Being able to find that least common denominator is going to be key in being able to find what's missing. Okay. So the least common denominator, you find the shared piece, if there is one, and then you add on the pieces that are not shared from each individual fraction. Okay. Now we need to work this part out. So I'm going to multiply out the numerator. I'm never going to multiply out the denominator. Okay. So 4x minus 20 plus 6x minus 18. All of that's over the same denominator, x plus 5, x minus 3, x minus 5. That's at LCD. And then I'm just going to simplify the like terms. 4x plus 6x is 10x minus 38. And the denominator stays the same. If I factored the top part with a GCF of a 2, it's still not going to cancel any of those down the bottom, so I just leave it alone. Okay, you got to think that in your head and see, okay, what's the top part factor as, if it will. A lot of times it won't even factor. This one just happened to have a 2 in common that you could pull out, but it's not going to cancel anything in the denominator. Now that. Let's look at another. Pretty heavy lifting tonight. 7 over x squared plus 4x minus 5 minus 10 over x squared minus 25. So before we could even find the LCD, what do we need to do with the denominators? Factor. And this is where being good at factoring is very helpful. What would the first one factor as? Positive 5, negative 1. Okay. Second one. Good job. Okay. That allows us to get the LCD once we get that. So least common denominator is what we're after next. What piece do I always start with? The one they both have. Both of them have x plus 5 in this one. And then I add on the parts that they don't share. X minus 5 and x minus 1. Doesn't really matter what order you put those in. There, as long as they're there. So then you look at it and say, okay, what's the first one missing of the LCD? X minus 5. So it needs an x minus 5 on top and bottom. What's the second one missing? and x minus 1. Okay. Multiply out the numerator, so that's 7x minus 35. And then this is a minus 10, so that's like a negative 10. So that's negative 10x plus 10 over the denominator, x plus 5, x minus 5, x minus 1. Okay. So I took this minus sign with the 10 when I distributed that. That's a kind of a trickery thing that they're going to throw that minus sign in there. If it's a plus sign, it's not going to mess with you. But if it's a minus sign, you want to say, oh, I got to subtract, distribute the negative with it to work that out. Okay. And then simplify the numerator. So that'd be negative 3x minus 25. There's no way that factors at all. We've added and subtracted some rational expressions.
Okay, so what was can you run that by me one time, the negative?
All right, if there's a minus sign right here, stick it with whatever's on top on the second fraction. And when you distribute like a negative 10 instead of just regular 10.
So just take it on.
Yeah, so it's like a negative 10 there, and then distribute that instead of just a regular 10. Yep. All right. Still in R5. We're almost done with R5. A couple more. 3 more examples in R5. The next thing that we do in R5 is this thing called complex fractions. Complex fractions are fractions inside of fractions. So it's the things they make Xanax for. Is the reason that drug even exists is because of these things. So let's look at why that's happening. So let's say 3 plus 4 over x squared. The good thing is with the complex fractions is they don't get too complex with you. They're already fractions inside of fractions, so they don't make the fractions that are in them very tough. So that's the maybe the saving grace of these. All right. So there's a complex fraction. That's what it looks like. You got a problem up top, you got a problem in the bottom, and it's just one big fraction. So the idea is that you need to work the top part, then work the bottom part, and then work the big fraction. So individual pieces. Okay.
On this lesson, it's just like, we're gonna make this student's worst nightmare.
No, maybe not. I don't know if they. I don't think any mathematician really thinks that way. Because to them, it's not a nightmare. It's math. So let's look at this one. So 3 written as a fraction would be 3 over 1, right? Okay, so I'm just looking at the numerator. Don't worry about the denominator yet. So if I'm going to add these two together and simplify that and make it one fraction, what would be the common denominator on the top? Denominator, not numerator. X squared. There's a 1 on one of them and an x squared on the other. The common denominator would just be x squared. So the 3 needs an x squared on top and bottom. So we end up with 3x squared plus 4 over x squared. And then maybe just let me put that big fraction bar there. And then we work the denominator. That's still 6 over 1. It's a very similar problem on the bottom. What would be the common denominator on the bottom? X squared. So the 6 needs what? X squared. So that's 6x squared minus 1 over x squared. Now, the fraction symbol stands for what operation? Divide. We're dividing two fractions. When you divide fractions, what do you do with the second one? Flip it and multiply. So if I do that, I've got 3x squared plus 4 over x squared times, flip it, x squared on top, 6x squared minus 1 on the bottom. And we're back to multiplying fractions again. Well, these can cancel each other, right? Those aren't, you can't factor these. So you can't cancel individual pieces because the one's plus 4 and the other one's minus 1. So they're not even the same. They're not alike. So it's just 3x squared plus 4 over 6x squared minus 1. So 1, 2, 3 steps. 4 if you count the simplifying, the canceling going on there. Not bad, not bad. Let's look at one that's a little bit, maybe a little more interesting. Example V. Getting on down in the alphabet tonight. 1 over x plus 1 minus 1 over x minus 1 over 1 over x plus 1 over x plus 1. Again, don't try to do too much at once. I say that a lot in this class. Don't try to do the whole thing at the same time. Okay, you can take your Valentine out to eat tomorrow night and you get the 32-ounce steak and she gets the 6-ounce filet. Don't try to eat all of the 32-ounce in one bite. It ain't gonna go, it's not going to end well for you. Okay? So take one piece at a time. So take the numerator, take the denominator separately. Work them separate first. So let's work on the numerator. What would be the common denominator on the numerator? Very good. So the first fraction needs what? It's already got the x plus 1, so it needs the x minus 1. That's x. All right, so the common denominator here for these two pieces, they don't share anything. They're two different factors. So there's not a shared factor. So the common denominator is just going to be both of them together. Okay? So the first fraction needs the one it doesn't have, the x minus 1. The second fraction is going to need the x plus 1. Okay? X minus 1, x plus 1. And then we have negative, that's just the x plus 1 on top, over x minus 1, x plus 1. Subtraction bar. And I'm not working on the bottom one yet. I'm not doing too much at once. Oh, that's how you end up crazy. All right. Top part, it's like I'm distributing a negative 1 to x plus 1, turns that into negative x minus 1. So that's going to be negative 2 over x minus 1, x plus 1. So this is the numerator up here. Okay. Negative 2 is what this simplifies here. X minus 1 minus x minus 1. Because you distribute the negative. So maybe I'll write that negative x, negative 1. That's how that's happening. And then we got big fraction bar. And now I can actually start working on the denominator. What would be the common denominator for those things on the bottom? And an x. Because this x plus 1, it's got the plus 1. So it really is not like this x. They're two separate things. Okay? One's an apple, one's an orange. They're not the same. Okay? So I'm going to multiply this one by x plus 1 and this one by x. So that's going to give me x plus 1 plus x, all that over x x plus 1. So I'm going to simplify the denominator. Negative 2 over x minus 1, x plus 1. That's the numerator that I'd already done. Big fraction bar. And then I have 2x plus 1 over x plus 1. But dividing by a fraction is the same thing as multiplying by its what? Reciprocal. So I have negative 2 over x minus 1, x plus 1, times x plus 1 over 2x plus 1. X plus 1 is going to cancel out. And that's all. So I have negative 2x over x minus 1, 2x plus 1. Complex fractions. They're complex. That's why they named them that. Okay. It takes being able to add and subtract fractions with unlike denominators. It takes being able to simplify and factor. It takes being able to flip the second fraction and multiply and simplify out of that. So the complex fractions is really the total of section R5. It just takes everything that you got to be able to do it. So they're pretty tough. Okay. 3.5 is easier. The next section is the easier stuff. It's still fraction stuff, but it's not as much heavy lifting as this is. It's not as much factoring involved. There's some, but nothing like this. Okay, so it's going to get easier before we get out of here tonight. All right. Okay. That's section R5. Let's go to section 3.5. Rational functions. We're going to talk about graphs a little bit. I'm going to open up my graphing calculator, let it be warming up, getting ready to go, because we're going to look at a few graphs of this. We're going to find a lot of things without graphing it, but I want to show you what it looks like on the graph when you do find them. Okay. Clear out some stuff that I had in here from earlier today. All right. Rational functions. Basically, what we're going to be finding is domain, range, and these things called asymptotes. Okay. ASYMPTOT. It's this imaginary line that creates boundaries for the graph. Okay. Asymptotes are related to domains and do this long division. Done long division with polynomials in 100. So we're going to pull that back out tonight and do that a little bit as we go here. But an asymptote is this dotted line that's going on. So like what it's going to look like is you may have this graph of some rational expression, and it's got a vertical asymptote there, and maybe it's got a horizontal asymptote here. And what it does is it creates this boundary for the graph to do something like this. It creates boundaries. The red part is the actual graph. The blue lines are your asymptotes. That the vertical one and the horizontal one. There's slanted ones. We'll talk about those tonight as well. But that's what an asymptote does. It creates like the walls that the graph is going to follow. Okay, the graph is going to go up close to those walls, but it can't cross them. It can't bust through them. Okay, so that's what an asymptote works like. So we're going to find out what those where those come from. Again, they're related to domain, so it's going to come from the denominator, and what x can't be is where that's going to happen. It's very much related to domain. And then we'll might have to do some long division, but long division only happens in certain cases. Domains every problem. Long division doesn't always happen, and I'll show you the rules for when that does happen. It's not. It's kind of like if you know the rules, then it's easy. If you don't know the rules, you're going to struggle. So we'll start with some review of some transformations of or on the f of x equals 1 over x graph. Okay, remember transformations are shift left so many units, up or down a certain number of units, vertical stretch, vertical compression, horizontal stretch, horizontal compression, some things that we talked about in 100 with that stuff. But kind of review that as we go here. So let's look at this. If the equation looks like this, let's say it was y equals 1 over x minus 2. It happened to the x. So it's kind of like it's on the inside. Remember, it's the opposite on the inside. So if it's a minus 2, that means it's going to move right. Yeah, positive. So it's moving to the right 2 units like that. Example B, if it were y equals 1 over x plus 5, that's happening on the outside. So that's vertical movement. So it's plus 5. So vertically, that would be up. So up 5 units. U's and ends look the same.
So horizontal is opposite.
Yes, absolutely. The same as you see. Yeah, yeah. Horizontal is going to be the opposite. Vertical is going to be whatever you see. All right. Y equals 1 over x plus 3 minus 6. So this one's doing 2 things. What 2 things is it doing? Good job. Easy. So it's just basically looking at the equation and recognizing what's happening. 4 over x plus 7. I agree with the up 7. What's the 4 on top doing? Maybe it makes it look more correct if I write it this way, but they're never going to write it that way. Multiplying by a number out in front of it, right? Because 4 times 1 over x is 4 over 1 times 1 over x would be 4 over x. What does multiplying by something out in the front do? It's a vertical stretch. If it's a big number, it's a vertical stretch. If that were a small fraction, it would be a vertical compression. So if it's like 1/3 times 1 over x, that's a vertical compression out of that. So being able to recognize those transformations that happen over the course of an equation. So they're going to start with something and say what's going on with it. All right. Now, so that's some basic things with transformations. Make sure you look back at that. So those are some easy give me things for quizzes and tests. The transformation parts should be give me stuff. All right. Let's look at the important parts of rational functions. So a lot of definition writing on this part, and then we'll get to the actual doing it. Okay. There's a lot of this is the set of rules that we live by. So the important parts of rational functions. Rational functions, remember those are fractions. That's what's going on. Okay, fraction equations is what we're dealing with. Obviously, something that we've talked about with every type of function that we've done is the domain. If it's a rational function, we did this in R5 at the very beginning. How do you find the domain? Set what equal to 0? The denominator. Set the denominator equal to 0. Okay? When do you do that?
First.
Before you do what? Before you simplify. Make sure that. That's very important, especially since we're dealing with domain of an actual graph of a function. That's a big deal. All right. After you found the domain, you want to look for vertical asymptotes. And again, those are the imaginary lines that show up with restrictions from the domain. Okay. Okay. So they usually match domain, but sometimes are canceled out. They're canceled out through the simplification process. Okay, so this is where after you found domain, you're going to factor top and bottom and simplify if possible. Okay, if it is canceled out, then the vertical asymptote won't show up, but that number would be in our domain. We're going to see that with some examples here. But horizontal or domain, then vertical asymptotes is the next thing you look for, because they a lot of times they're going to match. They're going to be the same. So like if you had a domain where x does not equal 5, then x equals 5 would be a vertical asymptote. That's what we're going to see, that they match up. And then there may be times where you may have two or three things in the domain, like x can't be 5 and x can't be 3. But then when you simplify the fraction, one of your factors cancels, so you only have one vertical asymptote instead of two. We'll see that as we go here. So vertical asymptotes is the second thing you do, and it comes from simplifying and then looking at what's left in the denominator. Usually it's going to match your domain. Okay. The next thing that we could have is a horizontal asymptote. Okay. When this happens is only if the degree of the numerator is less than the degree of the denominator. If that's happening, then the horizontal asymptote, and I'm going to abbreviate that HA, is y equals 0. Example of that would be something like if you had x squared minus 5 over an x cubed plus 5x squared minus 6, something like that. There's an example of that happening. The numerator's degree is 2, highest exponent. Remember that from 100. The degree is the highest exponent. Highest exponent on top is 2. Highest exponent on the bottom is bigger than that. So you automatically have a horizontal asymptote at y equals 0. You don't have to do any work. You don't have to solve it. You don't have to do anything. That automatically happens. That's one case for a horizontal asymptote. The next case is this. If the degree of the numerator is equal to the degree of the denominator. Then the horizontal asymptote is y equals, we'll call it A over B, the ratio of the leading coefficients. I'll write an example here off of the side. So if you had, y equals 4x to the third or plus 5x squared minus 6 over 5x to the third minus 8x plus 13. Just making it up here. The degrees are the same. So the horizontal asymptote is at y equals 4 over 5, the ratio of the leading coefficients. No calculating to do, no real work to do. Just by knowing that rule, you get a horizontal asymptote given to you. Okay, so domain, always there. Vertical asymptotes, always there. Unless they all cancel out, which doesn't happen very often. Horizontal asymptotes, two cases. Top is smaller than the bottom, then it's y equals 0. Top is equal to the bottom, degrees, then it's the ratio of the leading coefficients. Those are the only two times that a horizontal asymptote will exist. Domain's always there. Vertical asymptotes are usually always there. Horizontal asymptotes only happen when that's the case, not any other time. All right, that gets us to the last type of asymptote, which is called an oblique. And you'll hear me use the old term slant. Oblique and slant asymptote. We used to call them slant asymptotes. Is the way I learned it. They call them oblique now. It's the same thing. Okay, slanted. We call them slant because they're slanted. They're diagonal and not vertical or horizontal. They're diagonal. They're slanted. Oblique is what the buzzword is now. Oblique asymptotes. Here's when they happen. It's the only time they happen. If the degree of the numerator is one more than the degree of the denominator. Then you use long division to find the oblique asymptote. And notice I wrote y equals mx plus b. That's what the answer will look like. The oblique asymptotes will be a line in slope-intercept form. Horizontal asymptotes will be y equals a number. Vertical asymptotes are going to be x equals a number. Oblique asymptotes are going to be slope-intercept form. And we're going to get that from long division. Okay? This is the only time oblique asymptotes exist, when the degree of the top is one more than the degree of the bottom. An example of that would be f of x or y, whatever you want to call it. Maybe it was 4x to the fifth minus 6x to the third plus 8 over x to the fourth minus 2x to the third minus 8x squared plus 13. Because the degree of the top is one more than the degree of the bottom, we could do long division and find that oblique asymptote. We'll get some practice with that in a minute. This is not good. I just made it up. Just so we can see the degree difference. Okay. One kind of thing they don't tell you this in the book, but I'll tell you this because I want to help you out. Oblique and horizontal asymptotes do not exist together. Oblique and horizontals do not occur together. That's important to know. If you have a horizontal asymptote, you don't even have to think about finding an oblique. If you have an oblique, there's no way you have a horizontal. Okay? Can't happen together. There is a case where you have no horizontal or oblique, and that's when if the degree of the numerator is more than 1 greater the degree of the denominator. Then there is no HA or OA. Example of that, f of x equals x to the 7th over x to the 3rd. Numerator is much greater than the denominator. There's no horizontal or oblique out of that. Okay. All right. So we're going to take a few problems. 1, 2, 3, 4, 5, 6. 6 of them. And we're going to step through finding all of these things, and then we're going to look at the graph of each of them after we've done those things, so we can see what our graph looks like. But it's not. I think once you see it done with some problems, 6 problems, I think we should see everything that's going to happen. I think you'll start saying, "Oh, well, it's not that bad. All I've got to do is look at this, and that's going to tell me what to do." So if the definitions, yeah, it gets a little because using numerator and denominator on every one of them. Once you see it relating to a problem, I think it's going to make it easier for you. Okay, so let's look at a few problems. Here are our instructions. State the domain. Find all asymptotes and graph. And we're going to graph with the calculator. Okay, so that's our instructions. No idea what letter I'm on. E, maybe? Is that right? It was. No idea how I knew that. All right, f of x. X plus 1 on top. That's our numerator. What's the degree of the numerator? 1. The exponent on that x is a 1. So the degree of the numerator is 1. Okay, and then on the denominator, let's have 2x squared plus 5x minus 3. What's the degree of the denominator? 2. Okay, we need to know those two things. We'll get to that in a minute, but I just want to recognize those as we write the problem so that we can remember, okay, degree, we're talking about the exponents on the x. What's the biggest one for each one? So when we get there, okay? First thing I want to do is find what? Domain. That's the first thing I want to do. Before I simplify or try to do anything else, I want to try to find the domain. Okay, so I'm going to start with the domain. How do we find the domain? Set what equal to 0? The denominator. So I'm going to set 2x squared plus 5x minus 3 equal to 0. And because I'm in the rational functions part of the world here, how am I going to try to solve that? By doing what? What we've been doing all night. Factoring. That's what we want to use. That's going to help us. Okay? So we're going to factor that. -6 had to be 5. There you go. So 2x squared plus 6x minus 1x minus 3. Now group that. That's 2x, x plus 3. That one's got a -1 in common, so that's x plus 3 again. So I have 2x minus 1 and x plus 3 is my factored form of the denominator. And I set those equal to 0. And solving those gets me x equals 1/2 and x equals -3. Okay? So my domain is all x's as long as x does not equal those. There's my domain. I could write that in interval notation if I needed to. We'll do that anyway. -infinity up to -3, union, -3 to 1/2, union, 1/2 to infinity. Hopefully we're getting better at that, and that's getting boring doing that each time. Okay? Now, the next thing I find after I do the domain is vertical asymptotes. I always want to do those two together. Okay? The step in between those two is simplifying if possible. Okay? You always want to simplify after you find the domain if you can. Does this one simplify? So I'm using that factored form, 2x minus 1, x plus 3. Does that simplify at all? So the first thing you find is domain. Second thing, try to simplify. I'm kind of trying to give you a path that you want to go through. So first thing you do is find the domain. Second thing you do is try to simplify. Does anything simplify? No. If nothing simplifies, then you go straight to your vertical asymptotes. That's the next thing. Vertical asymptotes. Okay? All that hard work that we did to factor this, because it didn't simplify, we're going to use both of those. If it had simplified, and we'll see one later that does, then we would use the one that's left. Okay? Here, both of those factors are still in the problem, so we're going to have two vertical asymptotes. We're going to have one at x equals 1/2 and one at x equals -3. Okay? X equals 1/2 and x equals -3. All right. Next thing to do is look and see if we have a horizontal asymptote. So this is where we got to know our rules. Okay, so if we go back up here to our rules about horizontal asymptotes, there's two things that could happen. The degree of the top is less than the degree of the bottom. What's the degree of the top on our problem that we're working on right now? 1. What's the degree of the bottom? 2. It's squared. So 1 is less than 2, right? What's the horizontal asymptote when the top is smaller than the bottom? When the top is less than the bottom, it's always y equals 0. That is always, if the top has a smaller degree than the bottom, it's always y equals 0. I did. That's okay. You got to. There's a lot of rules that we wrote there, and you really don't see it until you start doing some problems with it. Okay, so if the degree of the top is small compared to the bottom, it's y equals 0. Okay.
So we don't even have to look for the oblique, right?
Perfect. That's right.
So we get to go to 10.
Yes. All right. So obliques. And I always write this in here anyway. The oblique asymptote, because there was a horizontal one, there's not an oblique. That's it. Okay? There's either going to be an oblique or horizontal. Never both of them. That's always the rule. Okay? All right. Example F. 5 more to go. Yeah, that's it. F of x. Oh, we got to graph it. Let's graph it. So I'm gonna type it in my calculator and look at the graph so you can see what those asymptotes look like. All right. So I'm gonna go, since it didn't simplify, I'm just gonna type the original problem in. So parentheses x plus 1 on the top, close the parentheses, divided by, and then I need to put a parenthesis in the bottom. So 2x squared plus 5x, and then minus 3. And then I'm gonna hit graph. And I've got my window messed up. I'm gonna fix it when it gets to graphing. Zoom 6. All right, some weird stuff looking there, right? Now, here's what I want you to see. Look at where these graphs get flat. What's happening right here? That's our horizontal asymptote at y equals 0. They get flat right there at y equals 0. That's that horizontal asymptote. Right here, you got some interesting things happening. This number is -1 to -3. What's happening at -3 on the x-axis? That was one of our vertical asymptotes, wasn't it? X equals -3. Over here, that's not 1, it's not 0, it's in between. That's our 1/2. That's our x equals 1/2. That's our other vertical asymptote. So those are the pieces. It doesn't draw them on the picture, but they're there. Remember, they're imaginary lines that kind of guide the picture in which way to go. That's what they're doing. Okay? Kind of like, ever try to herd cats? You try to push them into the, I don't know if you've ever heard of cats, sheep, or anything, any livestock animal. We grew up with cows at my dad's place, so that made sense that when things guided, we would line up panels to guide them into the trailer or into the barn, wherever we needed them to go. The panels are our asymptotes. This is what they look like. When you've got vertical asymptotes, there's going to be some breaks in the graph that right those spots. When you see it flattening out, you got to think, oh, there's a horizontal asymptote there. That's what you recognize with that. So there's the graph. We see it. Looks really nice. It's pretty cool to see that stuff in action. Okay, so I'm going to graph that on paper. I'm just going to show that. I don't know why it does that. That's annoying. But anyway. Oh, yeah. That's beautiful looking. Okay, so there's our graph. Okay, let's look at the next one. See what's happening. 4x minus 2 over x plus 1. Fairly simple, innocent looking graph or innocent looking equation. What's the first thing we're going to do? You mean the domain. And the domain comes from what? Doing what with the denominator? Yeah, setting it equal to 0. No factoring to do on this one, so there's it's rational function. There's no factoring to do, so that's nice of them. X can't be -1, right? Easy. Real, pretty boring here. Interval notation, negative infinity up to -1. -1 to infinity. Real boring. Nothing fancy about that domain. Well, since there was no factoring to do, is there any simplifying that happens? No simplifying. No factors canceling out. So that means my vertical asymptote, you can abbreviate these anytime you want to, is what? X equals -1. Wonderful. Absolutely beautiful. Horizontal asymptote. Does this fit one of the rules for it? What's the degree of the top? What's the degree of the bottom? 1. They're the same. What's the rule? If they're the same, well, oblique is the top is 1 more than the bottom. That's not what's going on. Horizontal is the numerator is less than the denominator. It's y equals 0. That's not what's happening. They're the same. Yeah, that's the ratio of the leading coefficients. So we go back down here to this problem. Yeah, 4/1. That's it. Y equals 4. Technically, it's 4/1. We're just going to put 4. Because it fit the rule where the degrees are the same. Take the leading coefficients, divide them. Simplify that fraction if possible. Okay? So if it's got a horizontal asymptote, what do we know about obliques? They don't exist. Darn it. If it's got horizontals, it can't have obliques. If it's got obliques, it can't have horizontals. Okay?
So if we had one of the denominator and the numerator, the degrees are equal, and the numerator is not, let's see, the denominator is less than the
Right. If the numerator is more than 1 bigger than the denominator's degree. So like if you had an x to the 5th power over an x squared, then that's no horizontal, no oblique. Okay. Obliques only happen if it's like x cubed over x squared or x squared over plane x. That's the only time obliques happen. Okay. Okay. So we're ready for example G. Oh, we got to graph that one. Don't forget. Don't forget to graph it, Isabel. All right, here we go. Parentheses, 4x minus 2 over parentheses x plus 1, right? That's the right equation. Hit graph. All right, a little tougher to see here because they're not mashed real close together. They got a little gap in between them. But we do see them flattening out right here at that horizontal. And then our vertical, when you see it flattening out right here at that -1. So we got a vertical asymptote at -1, a horizontal at +4. You can see that happening with that graph. Whoops. I just hit delete. That was dumb. Let's do this. Copy. And paste that. All right. Example G. Let's see what happens with this one. G of x is equal to x squared plus x over x minus 1. Seems innocent enough. Yet is it? Well, what's the first thing we're looking for? Domain. So we got to do that first. X minus 1 equals 0. X does not equal 1. From negative infinity to +1 this time, and 1 to infinity. That should be getting boring, finding the domain of things. We've been doing that a lot. Okay, so that should be getting boring, should be getting easy. Okay. Now, I look at the numerator, I see it could factor. It's x and x plus 1, but is it going to cancel? No. I mean, I look for that before I go to vertical asymptotes to see if I could simplify. I couldn't. The last one, it didn't have any chance of simplifying. So we didn't even really look at the factoring. Could have factored a little bit, but it didn't even get close to simplifying. Okay. So vertical asymptotes, I'm just going to abbreviate VA, would be what? X equals 1. Be careful that it's an equation x equals something to be a vertical asymptote. Horizontal asymptote. Does this fit the rules for horizontals? No. The degree of the top is how much? It's one bigger than the one on the bottom. So we know this one is going to be an what? Oblique. So we don't have a horizontal, but we do have oblique. And I'm going to, this is the first one we've had. I'm going to write out. It's fairly important. Oblique asymptote. So this is where we're going to do long division. Okay, long division. So we're dividing in 100. You were like, why in the world would we ever need to long divide polynomials? Welcome to the why. This is it. Okay, this is one of the reasons you would. Okay, so we're going to divide just like it's written there. We're going to take x minus 1 into x squared plus x. Okay.
So it's not going to be like the ones we had last year where it was like 15.
It shouldn't be. No, they're not nearly as mean in this section as they were when they were just trying to get you to do long division. It has a purpose. So, all right. So now we're taking what times x gets me x squared? X. And then we distribute x squared minus x, parentheses, subtract. X squareds go away. X minus negative x would be 2x. Technically plus 0. And then what times this x in front gets me 2x? 2. So plus 2 out there. So that's 2x minus 2, parentheses, subtract. Remainder is a 2. The part we care about is the x plus 2. The oblique asymptote will be y equals x plus 2. That's our oblique. Okay. Doesn't matter. The remainder, you just throw it away. You don't even use it. It is. It doesn't help us. Okay. The remainder doesn't matter. It's only what the quotient is there. Now let's look at the graph and let you see what an oblique does to the thing. Okay. So y equals parentheses x squared plus x divided by parentheses x minus 1. We hit graph. All right. Looks different, right? We can see the vertical asymptote happening. That's kind of the normal thing. We're used to seeing that now. We've seen 3 or 4 of those. Okay, so there's our vertical asymptote at 1. That seems, here we see it kind of flattening out at a slanted, an oblique way. If I want to graph the oblique asymptote and let you see where it would be, if I graph that, it'd be x plus, what was it, x plus 2? That's, if they drew the dotted line in there for it, that it's there, there's the oblique. We can see it flattening out as it gets close to it. So that's what it does to the graph. It guides it toward that. Okay? Pretty neat. That's it. Not too difficult though, right? If you know the rules about the degrees, this is not terribly hard. If you don't, it could be problematic for you, no doubt. All right, so paste that graph here. Shrink that down. Oh, that's great. All right. Let's do another. What letter are we on? H? Yes, H we are. Letter H. F of x. 3x squared plus 5x minus 7 over 6x squared minus 150. Oh dear. That's a big number. Oh gosh. Whatever should we do? What do we do here? Okay, find the domain. So what's the domain? How do we find the domain? Okay, so 6x squared minus 150 equals 0. Now what? Okay, 6 goes in 150? I don't know, I'm asking you. I think it does. Yeah, the 6, and then that factors as x plus 5, x minus 5. What happens to the 6, though, when we go to solve this? Technically, by division, it does. Really cancels out. So we get x plus 5 equals 0, x minus 5 equals 0. So we get x equals negative 5, x equals positive 5. Those are the things that x cannot be. So our domain is all x's such that x does not equal plus or minus 5. And that's not very much fun to write in interval notation, but we'll do it anyway because we know how. So there's our domain. The next thing we should try to do with each rational function is do what? Simplify. In between domain and vertical asymptote is the simplify step. You try to do it. Doesn't mean it'll work. Doesn't work every time. Doesn't work a whole lot, but you do have to try. Okay, so we're going to try to factor the numerator. 3x squared plus 5x minus 7. It's trinomial, so that'd be negative 21, and add to be 5. Is there anything that does that? 7 and 3 are only options. One's got to be negative, and that adds to be 4, not 5. So it doesn't factor. So I'm going to write this in factored form here because it can. What are our vertical asymptotes? X equals 5, x equals negative 5. Doesn't matter what order you write those in, that's it. Okay? Do we have a horizontal or an oblique? Or either? Okay? Horizontal because they're equal, so that would be at y equals what? Which would be 3 over 6, which is y equals 1/2 is what that reduces to be. Okay? So that means what about our obliques? There's none. Okay? Always write that as just a reassurance that I don't have any obliques. Okay? And you could graph that with your calculator if you want to check that out and see what's going on. Okay? Oh, no. The rules make it look rough, but if you know the rules, the work's easy. Okay? And then we could graph that if we need to. Let's go ahead and go to the next problem, see what's happening with it. Let's do this one. HI K of X equals. Let's do X squared plus 4X. I'll make that 7X. I'm making one up on the fly here. I didn't like the example that I've got written, so I'm just making one up. And then x squared minus 9. Yeah, that's a good one. Perfect. Beautiful. First thing we do. Should be getting boring at this point, guys. You're doing the same thing over and over. Yeah, because x squared minus 9, when you set it equal to 0, is x plus 3, x minus 3. So x equals negative 3, x equals positive 3. All x's such that x does not equal plus or minus 3. And then interval notation. Boring stuff here. Should be getting old doing that. Okay, so how do we simplify? Or does it simplify? Okay, the top part factors is x plus 3 and x plus 4. That's important. Absolutely. Good job. So it simplifies to that. So that means the only vertical asymptote I have left is x minus 3. So x minus 3 would be x equals positive 3. So here's one of those weird ones where the domain doesn't match the vertical asymptotes perfectly. So we hadn't seen one of those yet. That's why I changed the example I had. I wanted to. That was on my mind. So
What was the deciding factor on 3B?
That your x plus 3 canceled out when you simplified. So now you've got x plus 4 over x minus 3. So the only vertical asymptote you have is at where x minus 3 equals 0, which is the positive 3.
Okay.
Why? Yeah, the degrees match, right? So it's leading coefficient, 1 over 1. So the horizontal asymptote, y equals 1. Horizontal asymptotes are always going to be y equals whatever number. When the degrees are the same, it's the ratio. If the degree of the top is small, it's 0. And then, so that means oblique, there aren't any. Can't be. There's horizontals, there can't be obliques. Okay? Questions about that one? Okay. Let's go to the next one. Example J. F of x is equal to x squared minus 4 over x minus 2. Do the boring part. Domain. X doesn't equal 2, right? Negative infinity up to 2, from 2 to infinity. We're really good at domain now. Should be. You've been doing it a while. All right, next thing we do. Yeah, the top are factors. And what happens? Yeah, the bottom part canceled out completely. So if there's nothing left in the denominator, what do we have about vertical asymptotes? We don't have one. What about horizontals? Do we have a what's the degree of the top? No. It's 1 now, because remember the stuff canceled out. Just and then it's over 1, so there's no degree on the bottom. No, we don't have an oblique because we don't have, if we did the long division, there's no x left in the denominator at all. Okay, so horizontal, we don't have any. And obliques, we don't have any. Because the entire denominator canceled out.
So when there's no denominator left,
Then it's Nothing. Because the graph, we really have this equation. Was it what I call it? F of x or k of x or what? F of x is equal to x plus 2. That's the graph that we're looking at. It's not even. It doesn't even look like a rational function when we graph it. The simplified version of it, it looks like a straight line. It looks like an oblique asymptote itself. But the idea is if the denominator completely cancels out, then you don't have that. You don't have those stuff going on. You don't have vertical asymptotes. You don't have those. Sir? Got one more. I think. It was 6, wasn't it? Oh, yeah, because I swapped that one out, so we didn't have. All right, we are done. All right, we are done. So, suggested problems. Page, I want to do mention that on page 346, there's a summary box in your book that's really good. Glance at that sometime. I mean, it's a good box, especially like just to keep you organized. Maybe it's a good thing to shoot a picture of and have on your phone just in case while you're working this. In R5, starts on page 47. Anything from 1 through 78, any of those problems would be good things to practice before you try that Canvas quiz. Page 351, 1 through 106. Any of those would be great to practice as you prepare to take your Canvas quiz, which will be due next Monday. So we got lecture tonight, Canvas quiz over this stuff, due next Monday. We'll do labs next Monday, and then 2 more sections of material, and then Canvas quiz over that, and a test the next Monday, the 27th.
So 3 weeks from now.
Yeah, 3. Yeah, if you count this as week 1. Yeah, week 1, week 2, week 3 is the test. The Monday before spring break. So February the 27th is our next exam. Email me if you got questions. I'll be glad to help as much as I can. Point you to the various other things that might help you. I will post a link to the